So good morning, everybody. I hope you all had a good weekend and are ready to tackle this week. As I know, I'm sure with the midterm coming up tomorrow, that creates a little bit of stress and anxiety, but hopefully if you can attend the review session tonight and we can all discuss any issues or last minute questions that you may have so that you can feel a lot more confident going into tomorrow's test. Today we're going to keep it moving forward. We finished compressible flow on Friday, and so we're going to start discussing chapter 7, which is flow past objects. So with that in mind, I'll go ahead and start doing the lecture. Flow past objects. The first topic of discussion is drag and drag force. So a drag force is a resistive force in the direction of fluid flow by a fluid or exerted by a fluid on a solid object. Meaning if I have a system of flow and in that flow field, let's say I have an object, a little sphere. The fluid would exert a drag force on the object, and by Newton's law, the object would exert a drag force on the fluid. And we can quantify drag force using the following expression. F sub d, which stands for drag force, is equal to C sub d, which is our coefficient of drag, or drag coefficient, times the fluid density, times the fluid velocity squared, times A sub p, which I'll talk about here in a second, divided by 2. And I'll say where CD is our drag coefficient, rho is our fluid density, U is our fluid velocity, and AP is a particular type, excuse me, a particular type of area. It's the projected area. And the easiest way to understand and visualize the projected area is in this instant where I have this spherical object in my flow field, the projected area would be almost like a two-dimensional cutout of that object onto the flow field. So for the example above, this projected area would be simply a circle with a diameter d shown here. So for the example above, for illustration, AP would be pi times the diameter squared over 4. if I were to look at another illustration, let's say I have an object that looks like this, where my flow field would now look a little more like this. My projected area would be simply that, where if this was the length, this with the width, and we also had a height, what do you feel the projected area for this one would be?
Width times height.
Very good.
Dr. Lopez, could you consider the projected area to be essentially the shadow if
That's
the
a
fluid...
good illustration. Yeah, it's a shadow, right? It's a two-dimensional extrapolation of the three-dimensional object. It represents essentially the restricted cross-sectional area that's missing from the flow field and the maximum restriction that the flow experiences. And so, in general, we can say the projected area for spheres we already stated pi times the diameter squared over 4. For spheroids but are considered non-spheres, we can consider the projected area some length dimension times some effective diameter, similarly to what we stated above for our little rectangle. So, more often than not, when we're looking at drag force, we can easily identify fluid density, fluid velocity, and if we know the type of object in our flow field, we can identify the projected area. The issue or the point of contention often comes when trying to determine our drag coefficient. Rearranging our drag force expression, we can identify that our drag coefficient is 2 times our drag force divided by density, velocity squared, and our projected area. And we find that the drag coefficient is largely a function of 2 items, one being a phi or sphericity, and 2 being the Reynolds number in our system. Where the way we consider Reynolds number as well as the implications for laminar transition and turbulent flow change when we're looking at flow around objects as versus unrestricted flow. And so when we're looking at this, I'll say RA sub P, with particles in the mix, we can have our mass velocity times the diameter of the particles of interest over the viscosity equals our mean velocity times our density times the diameter of the particles of interest over our viscosity, where d sub P, diameter particle, or our characteristic length. And our phi value is our sphericity, which gives you an idea of how sphere-like our obstruction particles are in our system. And we can calculate sphericity as 6 times the volume of the particle over the surface area of the particle times its diameter or characteristic length. So I'll say particle volume S&P is particle surface area is particle diameter slash that characteristic length. Here I'll draw a line to differentiate these two discussions, even though they're related. I'll give you guys a second. And so what we find when we're looking at our system is, in general, a higher Reynolds number results in a lower drag coefficient. And we can visualize that by looking at this figure, which is a figure 7.3 on page 158 in your text. And we see that for a given Reynolds number, which is shown in the x-axis, we find our drag coefficient falls dramatically. Or when we're looking at the far right side, and which what we consider largely turbulent flow, we find that the drag coefficient actually approaches a constant value over an appreciable range, typically between 1,000 and 100,000 of Reynolds number. And for low Reynolds numbers, we find that we have an exponential relationship between our Reynolds number and our drag coefficient. Now, an intriguing thing happens at extremely high Reynolds number, which you can kind of start to see towards the tail end of the figure, is that there's an appreciable dip at extremely high Reynolds number in our system. And so why do you guys think that there might suddenly be a dip in the figure for Reynolds number?
The speed of sound, maybe?
No, not necessarily. It's a little unique. Any other ideas? It's a little tricky phenomenon that you see in systems, and it mainly occurs as a result of the boundary layers that exists on a system. So what we find is that when we're looking at flow around an object, we have an instance where there's a region just beyond the object where the fluid cannot necessarily, it's one of those issues where the fluid can't, hug the actual object to fill that void. And so what ends up happening is you have a whole lot of energy loss and eddy and vortice formations. However, at high enough Reynolds numbers, what you find is that you essentially get a thinning of the boundary layer due to the momentum flux that exists as the fluid moves around the object. And it's particular to an object of interest at what Reynolds number associated with the flow this boundary layer thinning happens. What it means is at high enough Reynolds number, this area of the vortice formation is greatly reduced. And that results in less drag that exists on a system. So to summarize, I would say at high Reynolds numbers, boundary layer thinning results in a reduced drag coefficient and drag force. There are some ways to artificially improve the onset, if I could type today. Or there are some ways to essentially produce this in objects of interest. For example, if I had a solid, perfectly smooth ball versus an irregularly shaped ball, I would find that we have reduced drag in the irregularly shaped ball. And you can find that this is going to be applied in a wide variety of sports. It used to be when you looked at, the easiest example is golf. In golf, the balls used to be originally perfectly smooth. And they found that essentially fresh balls didn't go quite as far as essentially worn in balls. Balls that had been struck a number of times, had imperfections and indentations, and these essentially inclusions and imperfections on the balls actually caused this reduction in drag, which allowed the balls to fly farther. And so that's why when you look at modern golf balls today, there's essentially the pattern designed of dimples on the balls such that they can take advantage of this boundary layer thinning without requiring unobtainable high velocities. You see the same thing applied to baseballs as well as a couple other balls in sports. So for the rest of us, we can rely on a few sets of rules to identify drag coefficients for our system. So I'll say drag coefficients for laminar, transition, and turbulent flow. Now, for very low Reynolds numbers, we have a special case. And this is for fluids or situations that we call creeping flow. And for this, we have what's known as Stokes' law, which says that our drag force can be written as 3 times pi times viscosity times our superficial velocity times the diameter of our particle. Which means for these systems, we can predict the drag coefficient in this creeping flow as 24 divided by the Reynolds number. And this applies when our Reynolds number is much less than 1. For moderate flows, or flows that we can consider laminar/transition, where our Reynolds number is between 1 and 1,000, we can state that our drag coefficient can be approximated as 18 times our Reynolds number to the negative 0.6. Follows that exponential that we saw in our figure. And this is more of a transition than a laminar flow, just due to the fact that when we look at flow past objects, the presence of the objects results in a greater propensity for essentially turbulence, vortices, and things like that. And so if we find that in these systems, transition and turbulent flow occurs at much lower Reynolds numbers. And so we would consider Reynolds numbers less than 1 to have a laminar characteristics, Reynolds numbers between 1 and 1,000 to be more transition in characteristics, and Reynolds numbers greater than 1,000, or I should say between 1,000 and approximately 200,000, or 2 times 10 to the 5th, we consider this to be turbulent flow. Excuse me, let me rewrite that. And for this, the good news is in this region, we have that plateau in our figure, and so we can approximate the drag force or drag coefficient as simply 0.44. And so if I jump us back to that figure, we find that for systems between that 1 and 1,000, if we're looking at spheres, we have essentially that exponential dependence. For flow much lower than 1, we find a different curve where Stokes' law can apply, and then between 1,000 and about 200,000, we have that constant region that we can approximate. Our value is about that 0.4. When we're looking at spheres, then we can correct any other types of systems using a sphericity correction. All right.
So these three equations we just went over apply to spheres, and if we have something else, we need to do a sphericity
Yes.
correction.
Yes. Yeah, for systems or objects that are not considered spheres, we would correct our drag coefficient.
So does that mean that these are only relevant to like perfect spheres, or is there a certain range that of like sphericity that you would say they're relevant to?
Can you repeat that? I'm
Yeah,
not
so
quite sure how you're what you're asking, if that makes sense.
like with these, you're doing your sphericity correction. Is there a certain amount of like give and take with how perfect a sphere is that you would say these are relevant or they're not relevant?
Well, they'll always be relevant because at the end, if things are sphere-like but imperfect, we can correct by calculating the sphericity and incorporating that in our calculations. It's just a correction factor. That's a direct function of the sphericity. And so even if something isn't, perfectly sphere-like, these can still apply. Does that make sense?
Yeah, I guess it's just like a rule of thumb, like at what value you would say like you really need to go in and correct.
Oh, in terms of making an assumption, even if it's not an ideal sphere?
Yeah.
That's a fair point. Anything I would say below a sphericity of about 0.9, you would definitely want to correct. But if it's 0.9 and above, this might get you a solution with reasonable accuracy. But when we look at systems like, it becomes more of an issue when we're looking at groups of systems, which we'll talk about packed flow and fluidized beds on Wednesday. And in that case, you'll always have to consider the sphericity. But what we're looking at now is more general, like a single solid object versus a multitude of solid objects. Any other questions or points of consideration? All right. Now let's move to our next point of discussion for the day, which is applying these concepts, but in a different sense, such that we can consider the determination of a terminal velocity. And so if I have a solid object that's falling under the influence of gravity, I can consider the fact that there's two forces involved in that system, both in the y direction, the force due to gravity, and the drag force of our object. So the question then becomes, how can we write a momentum balance on this particle, or on this object falling due to gravity? And for this, I want you to think about it and consider it. And why don't you spend a couple minutes talking with each other in some breakouts to see what you can derive in terms of momentum balance for this system. So I'll give you guys about 3 minutes to see if you can come up with an expression. So how'd it go? What did you guys come up with for your momentum balance?
Momentum in or out minus momentum initial plus the drag force minus the force due to gravity is equal to momentum accumulated.
All right, so you got momentum in minus momentum out plus what?
The drag force minus the force due to gravity is equal to momentum accumulated.
Okay. All right, I like that. So which of these terms can we neglect? Assuming this system is our object.
There's no momentum accumulating.
You are right. I'm gonna hold off on canceling it out because it makes some of my calculations easier here in a second. But you are right in that there is no accumulation of momentum. I would also say that there isn't any momentum in or out because I don't have any flow in or out of my system, that being the object. So I would state for this problem, I have drag force minus gravitational force is equal to that accumulation term, which I can write as the particle's mass times its change in velocity with respect to time, times its velocity times its change in mass with respect to time. Now, since there's nothing going in or out of the object, I would state that there is no change in mass. And so I would say the drag force minus the force due to gravity is equal to mass times acceleration, which I'll denote as A. Now, I already have an expression for drag force. FD is equal to what I stated earlier, CD times rho U squared A over P over 2. My force due to gravity is its mass times a relative difference between the object as well as the density of the fluid times gravity, which actually this is going to be the volume of the object. And its mass is going to be the volume of the object times its density. So if I plug these values in, what I have is my drag force, CD, rho F, because I'm looking at the fluid, times U squared, the projected area over 2, minus the force due to gravity, which this is, if I'm looking and assuming it's a sphere, this is, the volume is going to be pi d cubed over 6 times the relative difference between the solid and the fluid object times gravity equals its volume, which is pi d cubed over 6 times the density of the solid times acceleration. Now, if I do as I've done but in the past, solving for acceleration, which means dividing by that pi d cubed over 6 times the density, I'm left with kind of a hairy expression. Which says 3 CD rho F U squared AP over pi d cubed times rho s minus rho s minus rho f over rho s times g equals a. Now, if I remember the projected area as pi d squared over 4, I can then rewrite a as 3 times CD times rho f u squared divided by 4d rho s minus rho s minus rho f over rho s times g. Now, this is why I held off on that saying the accumulation was 0. Primarily because now when I have this expression for acceleration, I can say we have our terminal velocity when a equals 0, or u is equal to u sub t when a equals 0. And so if I set my acceleration to 0 and solve for my velocity, I have rho s minus rho f over rho s times gravity equals 3 CD rho f u sub t squared over 4 diameter of the particle times rho s. So if I rearrange everything and solve for the terminal velocity, what I find is the terminal velocity is equal to 4 times gravity times the diameter of the particle times rho s minus rho f divided by 3 times CD times rho f. And this gives us our terminal velocity expression. So I know more algebra. So with the rest of class time, let's take a look at an example. Oh, let me try to zoom. So for this example, I have a spherical hot air balloon with a diameter of 40 feet and a deflated mass of 500 pounds being released from air at 50 degrees. The gas inside the balloon is 200 degrees Fahrenheit. And so what is its terminal velocity of the balloon if the drag coefficient of the system is approximately 0.6? So this is an intriguing problem in that it involves terminal velocity, but it's a reevaluation of the momentum balance, in that in this system we actually have 3 forces that we need to consider, because nothing can be simple. So I've got my hot air balloon, my little basket. The temperature on the outside is what, 50 degrees F. Temperature on the inside, I believe, was about 200. And so I have to consider the forces involved in my system. So if I have a hot air balloon moving up, I find that both my force due to gravity and my drag force are happening in the negative y direction, which means there's a third force balancing those two out. So what do we feel that third force would be?
Buoyant force.
Our buoyant force. So in this system, I have a buoyant force equaling our drag force and the force due to gravity. And once again, in this system, I must identify each of these forces to solve for the velocity in my system. And the easiest way to do that is if my buoyant force is equal to my drag force and my force due to gravity, I can solve for my drag force by saying it's the buoyant force minus gravity. Primarily because the only force that's a function of velocity is my drag force. And so by solving for my buoyant force and my force due to gravity, I can then calculate my drag force. Then using my drag force value, I can extrapolate out the terminal velocity that I have for this system. So with that in mind, I know that my force due to gravity is the mass of the balloon times gravity, which is equal to the mass of the balloon that's empty plus the volume of the balloon times the density of the air in the system, or the density at 200 degrees F. So I need to calculate the density of the air at 200 degrees, which if it follows PM over RT, and if I'm looking at 1 atmosphere, I have 29 kilograms per kilomole. R would be 0.08205 liter atmosphere, cubic meters, atmospheres per kilomole Kelvin. And I have 200 degrees F. Which, how much is that in Kelvin? Approximately 366. And you guys like doing everything in terms of metric units, so I'll humor you. I get about 0.966 kilograms per cubic meter of air. And now if I also compared that with the density at 50 degrees, I would find my density is higher. Which is just 283. Doing this calculation, I get approximately 1.25. So I have these two densities to do the calculation. Oh, we're probably going to be out of time, so I'll go ahead and finish this up on Wednesday. Are there any last minute questions on the topics that we discussed today? We'll do a quick recap and finish up this problem on Wednesday. All right, if not, take care, guys. Have a great day. Don't forget, midterm is tomorrow night. this evening I'm going to host a review session to give you guys a quick rundown of everything in terms of that will be on the test, in terms of fair game, as well as answering questions, working examples with you all.
Will the review session be on this Zoom link?
I sent another Zoom link this morning in an email.
Okay.
So look for that email. If you didn't get it, shoot me an email and I'll forward it to you.
Thank you.
All right, no problem. Take care, guys. Have a great day.